Okay, take 3. I have already drawn my free body diagram at point H, which includes all the reaction forces in the X, Y, and Z, as well as the moments in X, Y, and Z. I drew on the dimensions with all the forces acting on it. I calculated my area right here to be 0.02 times 0.04, which equals 8 times 10 to the negative 4. And then I set up my load table, and I'm now going to fill that in. So for my 3 kilonewton load, my R in my I direction is going to be 0.15 right here. So this is 0.15. J is going to be 0. K is also going to be 0. My F is going to be negative 3 kilonewtons in the I direction because it's going into the I. So, and then 0 in the K, 0 in the J. And then this moment is going to also be pretty simple just because we only have I cross I, and that's going to come out to 0. So it's 0 across the board here. So now the 0.5 is going to have the same I as the other one. It's going to be 0.15, 0, and 0. And then for F, we are going to have our I is going to be 0, our J is going to be negative 0.5. K is going to be 0, negative 0.5 in the J because it's acting in the Y direction. And then now we're going to do I cross J, which is going to get us K. So we're going to do 0, 0, and then 0.15 times negative 0.5. That's going to get us negative 0.075. Yep, okay. So then now we are 2.5 kilonewton load. And our I direction is also going to be 1.15. J direction is going to be 0. And then our K direction is going to be 0.16. 0.16 because this piece right here, we go 0.16 in the K direction. Now our F is going to be 0 in the I, 0 in the J, negative 2.5 in the K because this 2.5 is going into the K direction. So now our M, we're going to do I cross K, and that's going to get us negative J. So we're going to do 0.15 times negative 2.5. That's going to get us negative 0.375. My calculator's a little messed up right here, but this is just kind of blocked out. So that's going to get us 0, 0, and then we're going to get a negative in our calculator, so we're going to get a positive in the table. So it's going to be 0.375. Next, we would do K cross K, but that's just going to equal 0, so we don't have that on at all. So then, now I'm going to find my reactions. My reactions are going to be Rx, Ry, Rz, Mx, My, Mz. And for these reactions, I'm going to be writing what cancels out what is already in the table. So for our Rx, we look at our I column here, and we have 3 kilonewtons to counteract. The J, we have 0.5 kilonewtons to counteract. And then the K, we have 2.5 kilonewtons. So for our Mx, we don't have anything in the X direction, so that's just 0. Oops, I messed up this. Sorry, this should be in the J column. So for our J, we have to counteract this positive 0.375, so this is going to be negative 0.375 kilonewtons times meters. And then in the K, we have to counteract this negative 0.075, so that's going to be positive 0.075 kilonewtons times meters. Okay, so next we go on to doing our stresses, our stresses and loads. So we're going to have Rx first. Our Rx is along our longitudinal axis here. This is our longitudinal axis. So it's going to be axial loading. And that can be calculated with sigma equals P over A. I'm going to draw a block here. we're gonna have our X direction here. We can have our Y direction here. We have point H on top here. And then I'm going to be drawing the reaction. So it's gonna be a positive 3 kilonewtons right here. And our stress in the X is as simple as negative 3 kilonewtons over, I'm using negative 3 because I'm using my p-value, and my p-value for my X is going to be 3 kilonewtons here, negative 3. So I have negative 3 kilonewtons over our area, which we found was 8 times 10 to the negative 4. This is going to be negative 3 over 8 times 10 to the negative 4. That is going to come out to be negative 3750, which makes sense because in the X direction, this is going to be in compression because the 3 kilonewtons is going to be pushing into the reaction here. So we have a negative stress, which will result in it being in compression. So now I'm going to draw the stress blocks for these. So I said they were in compression, so it's going to be going inwards. And that is going to be 3750 kilopascals. And that is all we have to do for our X. So now our RY. Our RY is acting on a lateral axis here. So that means it's going to be transverse shear. Oops. Transverse shear. And then again, I'm going to draw my cross section. And that is going to have my x-axis right here, y-axis right here. We have point H up top again. And then I have my 0.5 kilonewton reaction force going upwards in the y direction. So for transverse shear, we have tau equals VQ over IT, correct? Yes, yes. So now to calculate Q, we need an end view. And with this end view, I'm going to find that point H is going to be on the top here. And then we have, this is like our x-axis, and then our y-axis is kind of in the middle here. So to calculate this, we need an outwards area. And since point H is all the way on the outside, we don't have any area to find. So area is equal to 0. Thus, Q is equal to 0. Thus, our tau is going to be equal to 0. So there's not going to be any shearing stress on this spot from the Y force. So now I'm going to flip the page over and do RZ. So RZ is again going to be transverse shear, and that is again because it's a longitudinal, or sorry, lateral axis as opposed to a longitudinal axis like the x-axis was. So now we're doing transverse shear again. I'm going to draw my box. And then for this one, since we're looking down from the y-axis, imagine my pencil is the y-axis, our point H is gonna be on the very center here. And then we have a shearing force of 2.5 kilonewtons, or the reaction force of 2.5 kilonewtons in the z direction. So now I'm gonna draw another one of these end views. This is going to be the same kind of end view that we had earlier, where this is my neutral axis here. This is point H, and we are looking for this area right here. So again, we find that so our y bar in this case is gonna be I have to think about this for a second. Sorry, so our y bar is gonna be this is like our, I guess, our halfway point. So we're gonna try to find the centroid right here, and that is gonna be let me think here for a second. So our y bar is just going to be 0.02 over 2, or sorry, 0.01 over 2. And that is simply because we need to do half of what we already have. So, wait, hang on. I believe it's gonna be, oh, fuck, I don't remember if it's 0.01 or if it's 0.02. I believe it's 0.02, but we use our 0.01 because we want to have want to be inside of the half of it. So we're just gonna do 0.01. It's gonna be 0.005 meters, and then we do our area A bar, which is gonna be 0.04 times 0.02 over 2. And that is gonna be 8 times 10 to the negative 4 over 2. A bar is going to be equal to 4 times 10 to the negative 4. So thus Q is y bar A bar, which is going to be equal to 0.005 times 4 times 10 to the negative 4. And that is going to make Q equal to 0.005 times 4 times 10 to the negative 4. And that is going to give me 2 times 10 to the negative 6, I believe. Yeah, negative 6. Okay, so now that we have our Q, then we can calculate our tau. So our tau is just going to be VQ over IT, where our V is going to be 2.5 kilonewtons. Kilonewtons times 2 times 10 to the negative 6. This is going to be over 1 over 12 times 0.02. That is then going to be times our thickness, which is 0.04. And we're using our T. Our T is our, oops, shit, you can't even see that. Our T is our thickness, and we're going to be using our thickest part, which is going to be this 0.04 here. So then from there, I'm going to find, and then this is going to be in the XZ plane, the shearing stress, because the shear force is acting on the plane, and our H is on that XZ plane. So from here, I find that tau XZ is going to be equal to so I'm going to get 5 times 10 to the negative 6 over 4.26 times 10 to the negative 9. Put those over each other and I get 1171. 71.875, and that is going to be in kilopascals. Okay, so now I need to do my stress blocks. So that is going to have So I found that my shear stress was in the XZ plane, and it's a positive, so it's going to look like this. And this is going to be 1171.875 kilopascals. Just to draw those in there for continuity. Okay, so now we have completed all of the reaction forces. Now we're going to move on to the moments. So for mx, we found that mx was equal to 0. So mx equals 0. Mx was along the longitudinal axis here. So that was going to be torsion. But since mx is equal to 0, we have no torsion. Now we're going to move on to my. And my is along the lateral axis, and that is going to cause bending at point H. So this is going to be bending. And bending is equal to my over I is equal to stress. So drawing. So for the moments, I'm always gonna draw the axis that the moment is the axis that I'm looking about. So we're gonna be looking about about the y-axis. So we're gonna have x this way, z this way, and then point H right there. And then I'm gonna be drawing my reaction force. So that is going to be negative 375 kilonewtons times meters. So that's going to be going this way, negative 0.375 kilonewtons times meters. So our y in this scenario is going to be our distance from the central axis to our point. So in this case, there is no difference. Our point H lies on the x-axis. So our y is equal to 0, thus our stress is equal to 0. Which makes sense because it shouldn't be experiencing stress, especially in the y direction, because it's bending about point H, not bending into it or away from it. That's why it equals 0, because it's going around it. Okay, so now we have MZ, and this is also going to be bending because it's along the lateral axes. I'm going to draw this one like this. So I'm looking into the z-axis, so my x is going to be to the right, my y is going to be to the left, and then my h is going to be up on top right here. And then I had my reaction was what? It was positive 0.075. So then I'm going to have 0.075 kilonewtons times meters right here. We found this was m times y over I is going to equal stress. So our point H here is being pulled by our bending moment. So that means that it is going to be in tension, which means that the moment is going to be positive. So our stress in x is going to be equal to our moment, which we're going to do a positive, so it's going to be 0.075 times our y. We found that our y, we know that this distance here is 0.02, so our distance from the x-axis to point H is going to be 0.01, and that is all going to be over I, which is 1 over 12 times 0.02 times 0.04 to the third. Solving that, I'm going to do 0.02 times 0.04 to the third. Divide that by 12. And then 0.075 times 0.01. Divide those by each other. And I am getting 7,009. Let me see if this might just be a rounding issue. So yeah, so it could be a rounding issue. This could, so if you rounded it to further digits, it was going to be 731.25. I'm going to go with this one because it's more further rounded, and that is going to be in the x direction. So drawing the stress blocks for that, I'm going to have so this is going to be positive, so it's going to be in tension. So it's going to be out like this. It's going to be 731 kilopascals. Okay, so now we have solved for all of our stress blocks, here. So now we're going to combine them all. And let me get another piece of paper here. So now this is going to be combined. Let me draw these real quick. Oops. Okay, so then now I draw the block part. Okay, actually, wait, let me make this one a little bigger. Okay, so now I'm going to combine all of the stress blocks that I accumulated in here, all of these ones. So looking at the first one, I have 3750 in the XY and the XZ plane in compression. And then, but I also, we just found that I have 731 in tension. So I'm gonna need to solve those two. So we'll do 731 minus 3750, and that is gonna get us 3281.24999. So that is going to be in tension, so that's gonna be coming out of the x-axis. And that is gonna be 3281 kilopascals. And then we found, so that takes care of our stress in the X. Now I look at my shearing stress in the XZ. I see that that is equal to 1171, and that's positive. So this is 1171.875 kilopascals. And then these are going to be our combined stress blocks. So looking at this, we see that our XZ plane has the most stress in it. So that is going to be where we're going to find our principal stresses on. So now we have principal stresses, and that is principal stresses in our XZ plane, because that's where our most of our stress is. So we're going to say sigma 1 comma sigma 2 is going to be equal to sigma x plus sigma z over 2 plus or minus the square root of sigma x minus sigma z over 2 squared plus tau xz squared. So now solving this out, our sigma z is equal to 0, so that makes this a little easier. So we have 3281 over 2 plus or minus the square root of 3281 over 2 squared plus 1171.875 squared. So this is going to be 1640 plus or minus, this is going to be 1640.625 plus or minus and then solving out this section here, we get plus or minus 215.6. So then this then becomes my tau max. So my tau max is equal to 2015.6 kilopascals. And then my sigma 1 is going to be equal to 3656.28 kilopascals. Let's say 0.3. And then sigma 2 . And that is going to come out to negative, sigma 2 is going to come out to negative 374.975 kilopascals. And we'll just round this one up to 375.0 kilopascals. So we now see that our maximum stress is 3,656.3 kilopascals. Sigma 2 is 375.0 kilopascals. Tau max is 2015.6 kilopascals. And this all makes sense. Yep. So from our axial stress, we're getting stress in the x direction. This transverse shear is only acting on the axis right here, not at it's only acting on the neutral axis, not at this section up here. And then moving on, we have the transverse shear acting upon this neutral axis here. That's why we have the shearing stress. And then we have bending in this one. We don't have bending in MY because we're bending about our point for this one. And then for MZ, we're bending from the point, so we're stretching it and bending it more. And from there, we combined all the stress blocks into these. And then from those, we calculated our sigma 1, sigma 2, and our tau max. Thank you for a great season, or I guess fall.